Morning, students. This is our 8th session on chemical bonding, and today we're going to discuss lots of applications on hybridization. Today's class is totally application oriented, so you're requested to focus better. Well, you've been discussing about another important quality which makes us very noble and peaceful. So, what is that quality? Faultlessness. So, should not find fault in anyone. Okay. So, one should be free from fault finding attitude. One should be liberated from fault finding attitude. This fault finding attitude is very much there, very much actually. So, all the time we focus on others' defects, others' limitations. Yeah, that's the issue, right? Yeah. And we go to the extent of even finding fault in mother, father, brother, sister, very common. Okay. It's a kind of disease, actually, truly speaking. The fault finding attitude is ingrained in the heart. It is ingrained in our basic character. Very, very important. Because that has been cultured that way, finding fault in others. So, for example, you show someone that there is a building, actually, that's your building. So they say they find fault in it. Okay. Instead of, they may be having maybe some minor uh, uh, minor defect may be there, but they focus on that defect. So, for example, in a personality, you find a lot of good qualities, but they point out only one thing, right? For example, you studied in a 10th up to 10th class. Definitely in the schools and all, naturally, some issues will be there. Something may not be good. Instead of focusing on a lot of good things, focus on only bad things. Again, I will give the example of the fly and honeybee. So the fly, usually, even one corner garbage is there, and even 1 kilometer nice garden is there, the fly goes to the garbage only. Okay. He won't go to the flowers to get the honey. Similarly, even 1 kilometer garbage is there. A small corner, some fruit, some flowers are there. Naturally, the honeybee goes to the flowers only. It's very simple. So, in your mother and father, to start with, you may find defects. Nobody is perfect. Try to understand. But everybody is in the path of perfection. So faultlessness is also one of the divine quality. Yeah. Don't find doshas in others. Okay. Not dosha, dosha. Dosha means mistake. Okay. You find mistake, but nobody is perfect. Nobody. Because if one is situated in knowledge, they never do mistake. Yes. If you want to exhibit gratitude, you require knowledge. If you want to free from fault finding tendencies, you require knowledge. So knowledge is required. So what is the outcome of fault finding tendency? So that's very important. What is the outcome? Tell me. So you'll be boiling all the time. Yeah. So again, this pride, and already conveyed to you. It is the pride, the fault finding tendency born out of pride. See, some of the common motivations are given in this slide. Have a look. Gaining a sense of superiority. You find fault in others that you are good and you are great and others are wrong. Right? So most of the time we argue also. We don't respect what others are speaking. We don't consider. We don't evaluate what others are speaking. Very, very important. Yeah. Next. It is due to born out of pride, actually, superiority. So most of the times it happens that you want to prove that whatever you floated is right. Okay. Similarly, getting back at someone who has hurt us. Okay. Yeah. So you find fault in others. For example, in your class, one student is there. So the student has hurt you with uh, some odd language, okay, or sarcastically something commented. So what you do, you keep in your heart and you get back. That's what I've written here. The getting back at someone who has hurt us, and you get back. So and you get back and you find fault in. Even the other person is perfect in many ways. You find fault in others. Yeah. Next is asserting our position or belief as the best or the only way. That's what I'm saying. You feel you are the best. Your idea is the best. And whatever you do is the best. And whatever you feel is the best. And you want to prove and you want to basically try to impose on others. Right? And in the process, you find fault in others also. That is not good. So it's a very, very difficult. Getting rid of fault finding tendencies is very, very difficult. Try to understand. Yeah. Next is avoiding scrutiny of our own shortcomings. So you won't scrutinize yourself. You don't introspect yourself, your own shortcomings. You have some issues. That's what I'm saying. You do mistakes. You're made up of mistakes. And you never evaluate your mistakes. So your own shortcomings. Right? So first of all, find fault in yourself rather than find fault in others. So try to fault in yourself. Right? Yeah. That is one of the best way to become noble. Yeah. Find fault at what time I'm waking up. Today I've come late to the class. So find fault in yourself. Sri Ram, Varshita, you all come late to the class. So find fault in yourself. And how you're studying, how you're solving questions, how you're serving, okay, how you're educating your brothers and sisters, and how is your caring and loving attitude towards your parents and your brothers and sisters. Yeah. You find fault in yourself, that how noble you are in all respects, right? What is your concentration levels? Find fault in yourself, right? Very, very important. Find fault in yourself why you are short of your percentage, performance, I mean. So you can find fault in yourself, right? So this is the best way. So to direct inward, right? Outward and inward. So find fault in yourself. That is very, very important. Okay, then there is a chance that you become noble and perfect, right? Yeah. So today I explained about what is the cause of fault finding attitude. So it's because of pride, because of not identifying your mistakes and that your shortcomings and not working on them, right? And you want to prove yourself you are the best, right? Yeah, your idea is the best. What do you talk is the best. What do you feel is the best. What do you do is the best, right? So these are the some of the issues, right? So, and if you are humble, you never find fault in others and you give respect to others. The fault finding attitude, if you have, you never respect anyone. Gone. Yeah. So definitely now, if you find fault, how you respect others? Yeah. Try to understand. If you find fault, there is no chance of respect. So not finding fault is a symptom or a sign of respect. So don't find fault in others. Very, very important. Yeah. Practice this. Simply you're listening and leaving here itself. Yeah. You don't take bath in the morning. Find fault in yourself. Right? How unclean you are. Yeah, unclean mind and unclean heart. So maintaining the uncleanliness, find fault in yourself. So in our last session, You've been discussing about sp3 d2 hybridization. I've discussed up to sp3 d2 hybridization, right? Yeah. So today's class is very important. So I'm going to give a lot of applications. Have a look here. Let us see sp3 d3 hybridization. So naturally, in sp3 d3 hybridization, the orbitals which are participating are one s orbital, one px orbital, one py orbital, one pz orbital, one dxy orbital, dyz orbital, dzx orbital. So yes, p3 d3. Yes, one s is there, p3 is there, and d3 is there. This is the hybridization. These will be participating, and they get intermixed to give a hybrid orbitals of sp3 d3 type. So, and it gives rise to a pentagonal bipyramidal geometry. So this is a pentagonal bipyramidal. You can see here, pentagonal bipyramidal geometry. Try to understand this. So try to understand here, equatorial bonds are longer than axial bonds. Equatorial bonds are longer. I'll explain this. Listen carefully. You know, iodine molecule. This is iodine molecule. Iodine. Example is IF7. This is an example. IF7. Iodine has, you know what is iodine? F, Cl, Br, I. So fluorine means what is the electronic configuration? 2p, 5, 3p, 5, 4p, 5, 5p, 5. So iodine is 5p5. So this is 5s, this is 5p. Any doubt? Any doubt is there? No doubt. Fine. Now, how many are required here? 7 are required. 7 bonds are required. 7 covalent bonds are required, right? They are directional in nature. So I have to excite this. To get 7, I have to excite all the 3. All the 3. 1, all the thing. 3. These 3. 1, 2, 3. So excited here. Now you got 7. Now to this 7 fluorines will combine. Second. Yeah. Here 7 fluorines will combine and use a pentagonal bipyramidal structure. So this is IF7. Pentagon and bipyramidal. Right? So here, try to understand. Yeah. If you observe here, there is a bond angle 72 degrees. Now, let us observe here, all of you, stay focused. What is the bond angle in trigonal bipyramidal geometry? Anyone?
So 120 degrees and 90 degrees, sir.
So 120 degrees and 90 degrees. Very good. So here, what is the bond angle in a triangle? This equatorial triangle?
72 degrees and 90 degrees, sir.
Here 120 degrees.
120.
Listen very carefully. And here, how much? How much is the angle?
72 degrees, sir.
Yes. So here, what is the angle? 90 degrees. Here also 90 degrees. So they are 120 degrees apart means there is no problem. Here, axial bonds are closer. There is a repulsion. That's why here, try to understand. These are equatorial. So equatorial bonds angle is 72 degrees here. Here 120 degrees. So here equatorial bonds are longer. That's why repulsions are more. Here what are longer? Which are longer? Axial bonds are longer here. Is here. Because there is a repulsion. There is a repulsion. Axial bonds are longer here. Here which bonds are longer? equatorial bonds are longer. Why equatorial bonds are longer? Because the internal
Equatorial
bond angle is
bond.
72 degrees only. So there are two bond angles here. There are 70 to 90 degrees. Here 120 degrees and 90 degrees. So 90 degrees is common between axial and equatorial. This is axial and this is equatorial. That is common. Right. But here, equatorial and axial, you can see, if you see the equatorial, only equatorial, 120 degrees. If you see only equatorial, 72 degrees. And it is very close here. Naturally, there is a repulsion. Hope you understood this. So this is all about hybridization. Okay. Now, let us see the applications of hybridization. Now, I would like to give some examples of starting with SP hybridization. I am giving this weekend 90% questions from hybridization only. Both NEET and JEE, 90% questions. So particularly, so from this class you'll get. From this class itself, 70% questions will come. Listen very carefully. Now, let us see the first example. C2H2. This is called ethine. This is also called acetylene. Ethine is a UPAC name, International Union of Pure and Applied Chemistry. Acetylene is a common name. For example, your name is common name is Chintu, and the official name is something. Okay, something like that. Okay. Now C2H2. So now in C2H2, how many carbons are there? How many carbons are there? Why you are not interactive? So carbon, listen very carefully. Now write the excited state. Any problem? Two carbons are there. C2, na? Right. You have written the excited state. So far, any problem?
No, sir.
Very
No,
good.
sir.
Now let's have a look here. See, this is one carbon. This is one carbon. Okay. Now listen very carefully. How many hydrogens are there for each carbon?
Two, sir.
Two. Each
Each
carbon
carbon.
one, sir.
One. Good. So here, hydrogen, hydrogen, right? So that means these two will combine and forms sp hybridization. These two will combine and forms sp hybridization. So sp hybridization, what is the structure?
Linear structure,
Linear
180
structure,
degrees.
sir. 180
angle,
degrees
sir.
bond angle, sir.
Yeah. This forms, listen very carefully. This forms one sp hybrid. This forms one sp hybrid. Are you following? And this is forming what bond? CC bond. Are you following? These
Yes,
two are
sir.
forming CC bond. This is CC sigma bond. And this carbon, one carbon is forming one hydrogen with one hydrogen. And this carbon is forming with one hydrogen. This hydrogen. One is forming with this hydrogen. So in one, actually try to understand. In the sp, these two only are participating. These two are not participating. I told you already, only sigma bonds will be participating in hybridization, right? So I got a linear structure. Now see here, C,
Yes,
C,
sir.
H, H, linear structure. Now listen very carefully. These two will form pi bond like this. Listen very carefully. I'm giving another color. So black color I'm giving. So see, these are unhybridized. They are not participating in hybridization. So shall I call these as unhybridized orbitals? These two. So first thing, these forms
Yes,
one
sir.
pi bond. See, one pi bond is formed here. See, one pi bond is formed. This pi bond. Now, similarly, this will form another pi bond. This will form another pi bond. You can see here. This is a Z orbital. This is a Z orbital. So it is forming another pi bond like this. So another pi bond. So one pi bond, another pi bond. So you get like this C, C, H, H. So similarly, one sigma bond and another pi bond. This is a one pi bond. This is another pi bond. There is one sigma bond. And it is linear structure 180 degrees. It is sp hybridization. So you can see here in this, you can see this here. There is one sigma bond. There is a CC sigma bond here. Because this is overlap is sp-sp overlap. This overlap. Understood or not? This overlap is sp-sp overlap. Agreed or not? This overlap is sp-s overlap. Agreed or not? This is sp and this is s. If you don't understand, I'll explain again. Yeah. Because
Sir,
first,
can you explain again, sir?
yeah. See, first of all, one carbon, it forms one hybrid. This is sp hybrid. Another carbon,
Your voice is breaking. Yes, sir, it is breaking.
Say voice is cracking in between.
now is it okay?
It
Is
will
it
be
okay?
fine, sir. Afterwards, again, it will start to break, sir.
You tell me next time when it breaks. Okay. Now listen carefully. Now, this
Now
is
also it's breaking.
Now what's it breaking?
Now this is one sp orbital, hybridized orbital. This is another sp hybridized orbital. Now listen carefully. Now there is C here, like this. Mr. Monish, every day you are coming late. Now, this is, so this is sp, this is also sp. So this is sp-sp. I hope you understood this bond. Now, here hydrogen is formed. So this is sp, s bond is formed. And this is also hydrogen is formed. This is also sp, s is bond. So this is C, C, H, H, linear structure. And there will be two pi bonds, right? Two pi bonds are formed. Those two pi bonds are not participating in hybridization. So this one, this is one pi bond. This is how one pi bond is formed, like this. So how another pi bond is formed? Another unhybridized orbital. There are two unhybridized orbitals. This is how another pi bond is formed. So you got C, triple bond C, H, H linear structure. Any doubt? You need to practice. Yeah. Now, let us see carbon dioxide structure. Carbon dioxide. Another example for sp hybridization. CO2. So carbon, same thing. Carbon is, write the accelerated state of carbon. This is the accelerated state of carbon. Now listen carefully. Here, carbon requires two oxygens only. It requires two oxygens, right? So one oxygen, it forms a sigma bond. Another oxygen, it forms a sigma bond. So naturally, the hybridization should be sp only. So this carbon, okay, it is forming one sigma bond with one oxygen, another sigma bond with one oxygen. That's it. So try to understand. Take oxygen here. So oxygen electronic configuration is as follows. 2s2, 2p4. So listen very carefully. This oxygen is forming sigma bond. Similarly, there is one more oxygen is there. Agreed? One more oxygen is there. Two oxygens are there. Like this. So this also forming one sigma bond. So this oxygen is forming one sigma bond with this. I hope you understood. Now this will form pi and this will form pi. Now I'll teach you. This will form pi with one oxygen. I hope you understood. So try to understand here. See, first of all, this carbon orbitals gets intermixed first. There is intermixing of atomic orbitals of carbon leading to the formation of sp hybrid. This is sp hybrid. Okay. Now oxygen is having these oxygen. Now oxygen, it is forming one sigma bond. Oxygen is forming one sigma bond. Now try to understand. Oxygen is having unhybridized orbitals also, like this. Unhybridized orbital is there. Agreed? Now, carbon is having two unhybridized orbitals. I don't know if you have seen, observed or not. One, two, three, four. So these two are forming sp. And these two are unhybridized. So this carbon, it forms a pi bond. This sigma bond is formed already. This forms a sigma bond with one oxygen. Now it is forming pi bond here, like this. Pi bond is formed. So pi bond is formed with this stuff. Now let us take here another oxygen. Here another oxygen is there. So another oxygen, it is forming another sigma bond. So this is another oxygen, sigma bond is formed. This is sigma, right? Sigma bond is formed. Now oxygen is having one more orbital like this. And this orbital is pz. This forms a pi bond. I hope you understood this. So this is py, this is pz. So this is py, this is py, and this is pz. So pz, it is forming with pi bond with another oxygen. So it is forming one pi with one oxygen, another pi with one oxygen. So carbon, when it is forming pi bond with one oxygen, it is using py orbital. And when it is forming with another oxygen, it is using pz orbital. Pz orbital. And only sigma bond should be participating in hybridization. That's why C, only this is considered sp hybridization. That's why it is sp hybridization. So it is linear structure. 180 degrees bond angle, sp hybridization, it is linear structure. Now you can see here the drawing here. So it is forming one sp, spp. This is spp. This is also spp because oxygen is using p orbital, right? And now that's it. Remaining will be pi bonds. So pi bonds won't participate in hybridization. This is a pi bond. This is a pi bond. So let me know if you have any doubt in carbon dioxide and C2H2. Any doubt? No doubt. Fine. So let me explain SO2. Listen very carefully. SO2. Very important and complicated slightly. So sulfur is this way. (3H2 3B4). This is sulfur. 3H2 3B4. This is 3B4. And write the excited state of sulfur. And because you know very well, sulfur is having 3d orbital. Second orbit is not having d orbital, right? So now excite this electron. This electron you excite. Now you get like this. Now you got a sulfur. Listen very carefully. Sulfur. This sulfur is forming one sigma bond with one oxygen. So one sigma bond with one oxygen. Agreed. Listen carefully. This sigma bond is formed. Now another sigma bond with another oxygen. So this is another oxygen, another sigma bond is formed. Right. That's it. Only sigma bonds will be participating in hybridization. So it is sp2 hybridization. sp2 hybridization. See here, one lone pair is there. This is a lone pair. This one is a lone pair. Lone pair means not participating in lone pair. Right. Now, this forms a pi bond, which is not participating in hybridization. Pi bond. One oxygen, pi bond will be formed. So it forms a pi bond. Now try to understand here one important point is that many times asked in the complex examination. This pi bond is called p pi bond. See, this is called p pi. Why? Because oxygen is having p orbital, and sulfur is also using p orbital to form a pi bond. So when p orbital is used, then it is called p pi pi bond. Now next one, another oxygen. This is another oxygen. It is forming d pi p bond. So how many d pi are there? This see, another oxygen is forming pi bond. What type of pi bond? Because this is a d orbital. So that's for d pi and p pi. So there is one d pi p pi bond. There is one lone pair. So this sp2 hybridization actually should have trigonal planar structure, but there is one lone pair. If one lone pair is there, it forms a V shape or a bent shape. Very important. So now listen carefully. I'll give one formula for you. H is equal to half into P plus M minus C plus A. With this, you will understand very easily. For example, SO2, have you understood SO2? Any doubt? No doubt. Okay. Now, I give one formula for you. H is equal to half into V plus M minus C plus A. Now, listen very carefully. Half. Let us take BeCl2. Beryllium, what is the valency? V means valency. Beryllium valency is 2 plus M means number of monovalent ions. Monovalent is how much? Chlorines, 2 chlorines are there, so 2. Minus charge on the cation is 0. Plus charge on the anion is 0. There is no charges here. It comes out to be 2. So 2 electron pairs means hybridization is sp. And it is linear structure, finished. Now let us see CO2. Just now you did it. So H is equal to half into V plus M minus C plus A. Now half into carbon is 4. Oxygen is divalent atom. So, but here monovalent atoms you should write 0. Number of monovalent atoms is 0. Halogens are monovalent. Hydrogen is monovalent. So minus C means 0 plus 0. Charge on the cation, charge on the anion. So answer is 4 by 2 is 2. So all the 2 electron, so that's why is sp hybridization. Here. Now let us see another one. SO2. SO2 let us see. H is equal to half into V plus M minus C plus A. So half into valency of sulfur, how much? Valency of sulfur, 6. So oxygen is a divalent atom. So number of monovalent atoms is 0. Minus charge on the cation plus charge on the anion. So total is 3. Listen very carefully. Out of 3 electron pairs, only 2 oxygens are there. So one lone pair will be there. Out of 3 electron pairs, so 2 oxygens, that means 2 bond pairs are there, 1 lone pair. So out of the 3 electron pairs, so 2 BP are there, plus 1 LP are there. It leads to angular structure. That is how we can answer. Similarly, SnCl2 you take. H is equal to half into tin, what is the valency? Carbon, silicon, germanium, tin, lead. So tin is plus 4. valency. 4 plus number of monovalent atoms is 2. Minus charge on the cation plus charge on the anion. Answer is 3. 3 means it is sp2 hybridization. So out of 3 electron pairs, so only 2 are bond pairs. That's why SN, 1 lone pair, 2 bond pairs. It is what structure? Bent structure. So how do you know? You can do hybridization concept. SnCl2, shall we see? Yeah. Now, tin. Tin is like this, like carbon only. I'm writing directly excited state. Miss Bhavya? Miss Bhavya?
Yes, sir, I have rejoined.
Now you can see here. T is excited state. Right? Now, try to understand. How many chlorines are there?
2, sir.
See, listen carefully. Very important here. Carbon, silicon, germanium, tin, lead. So, this is 2s2, 2p2, 3s2, 3p2, 4s2, 4p2, 5s2, 5p2. Now 5s2, 5p2. So, this is 5s and 5p. I have written the excited state. Now, ground state. This is the ground state. Listen very carefully. This is a ground state configuration. This is a ground state. Now here the question, SnCl2, that means only 2 electron pairs are required. So that is excited state is not required here. Because already 2 electrons is sufficient here. Here it is sufficient. I hope you understood. That's why it is participating. These are participating in hybridization. One s orbital, px orbital, and py orbital. So it leads to sp2 hybridization. I hope you understood. So this I'll write again for you. So tin is like this. 5s2, 5p. Now this is paired. Now these 3 will be participating in sp2 hybridization because this one chlorine, another chlorine. Now Sn, one lone pair is there. Check out here. Actually, it should be trigonal planar structure. So this is the structure. So out of 3 bond pairs, 2 are out of 3 electron pairs, 2 are bond pairs. So H is equal to half into V plus M minus C plus A. Half into valency is 4, number of monovalent atoms 2, totally get 3. So in these 3 electron pairs, this is called EP. EP means total electron pairs. So 2 are bond pairs. This is one bond pair, this is one bond pair, and one lone pair. So if all the 3 are bond pairs, all the 3 electron pairs are bond pairs, then what happens? It is trigonal planar. I'll give an example for you. For example, BCl3, AlCl3, BH3. Let us take these things, BF3. These are asked in the examination. So H is equal to half into valency is 3. Number of monovalent atoms are 3 in all cases. So total it comes out 3. 3 means trigonal planar structure. Because all 3 are bond pairs here. In SnCl2, what happens? You got 3. 3 is electron pairs. But how many bond pairs are there? Only 2. And 1 will be lone pair. Hope you are clear. Now, any doubt? Similarly, I'll give one more example for sp2 hybridization. Then we get into sp3. sp2 hybridization. I'll give one more example. C2H4. C2H4 is called ethylene. The IUPAC name is ethylene, official name. So ethylene. Ethylene is called common name. So let us see C2H4 structure. So C2H4. How to arrive at this? Very simple. Let us take first one carbon. First carbon. Write the excited state of this carbon. So excited state. This is excited state. Next, another carbon. 2 carbons are there. Write the excited state. Now listen very carefully. Listen very carefully. C2H4. That means each carbon requires two each carbon. C2H4 means like this. It's like this. Each carbon 2 hydrogens. So actually one carbon-carbon bond will be there. So it forms sp2 hybridization. So listen very carefully. sp2 hybridization, 1 carbon. What is the hybrid? Trigonal planar structure. Can you see a trigonal planar structure here? Yeah. Trigonal planar structure. Now, another carbon is also forming another trigonal planar structure. Like this. sp2. This is also sp2. So this carbon is sp2. This carbon is also sp2. Okay. Now let us see. So these will combine. How these combine? As follows. So this carbon is forming sp2. Listen carefully. And this carbon is also forming sp2. Now, there is one CC bond. First thing. This is the CC bond. One sigma bond is formed. So this is sp2 overlap. Okay. Now, this is one trigonal planar. Now, how many hydrogens are there? Each is having 2 hydrogens. So, each is having 2 hydrogens. So, this is having 2 hydrogens. H. This is having 2 hydrogens. So, trigonal planar. So, bond angle is 120 degrees. Now, listen carefully. This forms pi bond. So, this one I am showing you here. This is going to form unhybridized orbital. This is called unhybridized orbital. Is going to form pi bond. Now, this is the structure. C double bond C, H. So this is sp2. This is also another sp2. 120 degrees bond angle. Any doubt? No doubt. Good. Yeah. Now I'll give another example. Slightly. CH3 plus. What is the structure? How do you know? Very simple. H is equal to half into V plus M minus C plus A. So half into valency is 4. Next, number of monovalent atoms will be 3. Minus charge on the cation is 1. Charge on the anion is 0. It comes out to be 3. So naturally, 3 means trigonal planar structure. So C, H plus. So TP means trigonal planar, bond angle is 120 degrees. So this is how wonderfully you can answer. Now let us see. sp3 hybridization. Examples. Now listen. First example, CH4. H is equal to half into V plus M minus C plus A. So half into valence is 4. Number of monovalent atoms are 4. So it comes out to be 4. Charge is 0. So for all 4 are bond pairs. So it is tetrahedral structure. Right. All 4 are bond pairs. Only CH4 are there. Right. Same thing I'll give here with a water example. Ammonia, you take ammonia. Okay. Let us take ammonia. H is equal to half into valence is 5. Number of monovalent atoms are 3. Minus charge on the cation, charge on the anion 0. It comes out to be 4. Listen carefully. Out of 4, how many are bond pairs? 3 only. So 1 lone pair is there. So ammonia has 1 lone pair like this. So it is having pyramidal structure. Already explained to you. 4 electron pairs, 1 bond pair, 3 bond pairs, 1 lone pair is pyramidal. Now water molecule, let us take water molecule. So water molecule, help me. Water molecule, how to do? H is equal to half into V plus M minus C plus A. So here half into valency is oxygen, 6. Number of monovalent atoms, hydrogens are 2. So charge is 0. Now it comes out to be 4. Out of 4 bond pairs, only 4 electron pairs, they are electron pairs, EP. Only 2 bond pairs are there. So 2 bond pairs are there out of 4. So there will be 2 lone pairs. So it is bend shape. Bend shape. Let me know any doubts you have regarding this. Any doubts? Come on.
Sir,
Yeah.
sir, could you explain about pyramidal structure, that ammonia one more time?
Ammonia 1. See?
Yes, sir.
Ammonia is NH3. Use the formula H is equal to half into V plus M minus C plus A. So half into what is the valency of nitrogen? 5th group, na? 5. Monovalent atoms are hydrogens, 3. That's it. Charge is not there. So it comes out to be 4. So in ammonia, out of 4, only 3 bond pairs are there. These are electron pairs. Bond pairs are only 3. So actually 4 means what tetrahedral structure you write first. Bond pairs are 3. There will be 1 lone pair. So pyramidal. Any doubt? So whatever 4 you are getting, that is electron pairs, EP. So ammonia requires NH3 means what? 3 bond pairs are required. 3 bonds only it will form. So when out of 4, 3 bond pairs means naturally by default 1 lone pair will be there. So when there is a 1 lone pair, it leads to pyramidal structure. That is the basic thing. For example, NH4 plus H is equal to half into valency 5 plus 4 minus 1. Charge on the cation plus charge on the anion. Comes out to be 4. So all 4 are bond pairs here. So nitrogen, H, 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 H plus. This is how you get tetrahedral structure. NH4 plus is tetrahedral structure. For example, NH2 minus, let us see, H is equal to half into nitrogen is 5, hydrogens are 2, minus charge on the cation 0, plus charge on the anion is 1. Comes out to be 4. So out of 4, listen very carefully, 2 only are bond pairs. So 2 bond pairs. So definitely remaining 2 will be lone pairs. So bend structure. Bend structure. Next, you take here CH3 minus, H is equal to half into valency 4, number of monovalent atoms 3, charge on the anion is 0, charge on the cation is 0, charge on the anion is 1. CH3 minus the 1 here. It comes out to be 4. Out of 4, 3 are bond pairs. CH3 is there. 3 are bond pairs. So C, 3 are bond pairs. So 1 lone pair will be there definitely. So this is the CH3. So this is pyramidal structure. Now let us see another example. H3O plus. H is equal to half into valency is oxygen 6 plus number of monovalent atoms 3 minus charge on the cation is 1. Charge on the anion is 0. It comes out to be 4. Out of 4, 3 bond pairs are there. So oxygen is having 3 bond pairs. Hydrogen, hydrogen, hydrogen. That means out of 4, 1 will be lone pair. So H3O plus is pyramidal structure. So that means NH3 and H3O plus and CH3 minus. They are isostructural. Iso means same. Isostructural. Isostructural means having same geometry. Are you getting or not? Yeah. So this is how SnCl4, for example, which is equal to half into carbon, silicon, germanium, tin, lead. So valency is 4. 4 are there, monovalent atoms. So RC is 4. So definitely 4 means tetrahedral structure. So all 4 are bond pairs. All 4 are bond pairs. So tetrahedral structure. This tetrahedral structure. Now let us see another example, interesting example. SO3. SO2 we have seen. SO3. H is equal to half into 6 plus 0. Number of monovalent atoms are 0 because the divalent atom, oxygen is divalent. So 3. So that means SO2 and SO3 both have having sp2 hybridization only. SO2 also you write here. 1 second. SO2. H is equal to half into 6 plus 0 only here also. That is 3. But here out of 3, how many bond pairs are there? 2 only.
2, sir.
So 2 bond pairs. O. So 1 lone pair will be there. That's why bent structure. Here, how many bond pairs are there?
3 bond pairs, sir. No lone
All the
pairs.
3 are no lone pairs. So it is diagonal planar structure. This is bent structure. This is the difference. Both are hybridization is same. Yeah. But in SO3, listen very carefully. SO3 very interesting. Sulfur write the excited state. Directly I'm writing the excited state. They asked in the examination once how many d-pi p-pi bonds are there in SO2. Now write the excited state here. This is excited state. Okay. Now listen carefully. This one oxygen, the O1, I'm writing O1. This is O1. These 2. This third oxygen. So first oxygen, second oxygen, 3 oxygens. These 3 form sigma bonds. These sigma, sigma, sigma. Now again O1, O2, O3. This forms pi. This forms also pi. This forms pi. These are the things. Pi, pi, pi. But there are 2 d-pi p-pi bonds. So in SO2, there is 1 d-pi p-pi. In SO3, there are 2 d-pi p-pi bonds. These are the chemistry, very, very important chemistry. Any doubt regarding this? So in sulfur SO2, this forms sigma bonds. Sigma, sigma, sigma. Next it forms pi bonds. So what is the pi bond? This pi bond is p pi p pi. And this pi bond is, these 2 pi bonds are d pi p pi in SO3. This should be the understanding. Now I explained the shortcuts also up to sp3 hybridization. I explained for you. Okay. For example, BF4 minus. For example, BF3, it takes one F minus, forms BF4 minus. BF3 is sp2. Now find for BF4. H is equal to half into boron is 3, fluorine is 4, minus charge on the cation, plus charge on the anion. So total 4 is coming. Out of 4, all the 4 are bond pairs. So BF4 is tetrahedral structure. Tetrahedral structure. But initially, this BF3 is like this. Trigonal planar structure. This is sp2. Diagonal planar structure. It is converted into sp3 tetrahedral structure. Similarly, if you take AlCl3, AlCl3 is sp3 hybridization, sp2 hybridization, trigonal planar, sp2, and add Cl minus, it forms AlCl4 minus. AlCl4 minus. This one, AlCl4 minus. See, here H is equal to half into aluminum is 3, chlorines are 4, minus charge on the cation plus charge on the anion. It comes out to be 4. All 4 are bond pairs, so tetrahedral. So this is sp3. Simple. These type of questions will come in the exam. So competitive part I explained up to sp3. And tomorrow's class is also highly rated class. So tomorrow we see online. Okay. Yeah. Offline. So I open the session for discussion. Any doubts? Any doubts? Come on. Okay, fine. Thanks for bearing. Have a good day.
Thank you,
Thank you, sir.